Hello, chemistry. Mr. Decker here. I'm here today to help you understand light spectra. Let's take a look at what light spectrum is. If you have something like a light bulb, it emits what's known as white light. White light is a form of light that contains all the different colors and therefore all the different wavelengths of light. If we take white light and we send it through a prism, we can split that light into its different colors: red, orange, yellow, green, blue, and violet. You've probably seen this before. If you've ever been outside after it rains and the sun comes out, you'll see what's called a rainbow. A rainbow occurs because white light from the sun is being split up by raindrops acting as a prism, and the rainbow you see is the resulting spectrum of light. However, not all spectrum of lights are the same. For example, if you have a hydrogen gas discharge tube, you can see the spectra for hydrogen. If we take hydrogen gas and put it in a tube and then run an electric current through it, it emits light. If we take that light and split it up using a prism, we can see the spectrum for hydrogen light. It contains red, blue-green, blue-violet, and violet. Every element on the periodic table emits its own spectra. Let's look at how spectra can be used to explain the properties and the structure of different elements. Let's take a look at another property of light. Light is a form of energy that exists as a wave. All waves have what's called a wavelength, which is defined as the distance between the top of one wave and the top of another. Because light is a form of energy, there is a relationship between the amount of energy and the wavelength of light. As the wavelength of light decreases, the amount of energy that that particular wavelength has increases. So as you decrease your wavelength, the amount of energy contained in that particular wavelength of light increases. Let's take a look at the emission spectra for two different elements, hydrogen and boron. Notice that each element emits a different number of spectral lines. This means a different wavelength of light. For example, hydrogen has 4 spectral lines: 410, 434, 486, and 656. Each one of those is a specific wavelength of light that hydrogen gives off. Boron, however, has 8 spectral lines. This can be useful in identifying elements in an unknown substance. You can think of it like your fingerprint. Everybody's fingerprint is different than everyone else's. In the same way, spectral lines for an element are different than every other element's spectral lines. This can be used to identify the element. Okay, so we know that different elements emit different wavelengths of light. Let's look at how an element can emit light using our understanding of Coulombic attraction. We know that if an electron is on the first ring of hydrogen, it feels an attraction to the positive protons in the nucleus. Therefore, if we wanted to move it to a higher energy level away from the nucleus, we would need to use some energy to move it there. You can think of it kind of like a magnet. If you had a magnet close to another magnet, you would need to use some energy to pull it away. In this same way, once the electron is out on this second level, it has higher energy that it's received from the electric charge, the current that we gave it. However, that electron doesn't want to be on that second energy level. It likes being close to the nucleus. Therefore, that electron is going to drop back down to that first energy level. When it does, that energy needs to go somewhere. It releases it as light. Because the distance between these two rings is always the same, the energy that's released is always the same. Therefore, the wavelength that is released will always be the same. This is why hydrogen only emits specific wavelengths. The other wavelengths of hydrogen can be explained by looking at different transitions of electrons. In our first example, hydrogen had its electron move from the first level to the second level and then back down. However, there's 6 whole levels here, which means we have a lot of different transitions. If we were to give our electron a lot of energy and pulled it very far away from the nucleus, we could have it move to an even higher energy level. This higher energy level will cause the electron to move back down to the first level it was at, and again, it's going to emit energy in the form of light. However, remember, we gave it a lot more energy than we did before. Therefore, it's going to release a lot more energy than it did before. When it does that, we get a wavelength that is much smaller than our previous one. Remember, wavelength and energy are inverse. The higher the energy, the smaller the wavelength. Since it takes more energy to move an electron from a ring close to the nucleus to one farther from the nucleus, transitions that cause the electron to move a greater distance will always release more energy. Therefore, the shortest wavelengths of the spectrum correspond to the biggest transitions. The longest wavelengths, which have the least energy, correspond to the smallest transitions.